Hello everyone. Today I am going to explain about characteristic impedance of a symmetrical pi section. Okay. First of all, we'll see what is a symmetrical pi section. So as we know that a section is nothing but it has consist of one series impedance value with the one shunt impedance value. So whereas if we consider a T section, so it has a two series impedance values with a one shunt impedance value. So whereas in pi section it consists of one series impedance with a two shunt impedance value. And we are seeing it is a symmetrical pi section, means whatever the input impedance presented across your output, that should be equal to your input. That's why we are saying it is a symmetrical pi section. Okay. Today we are going to derive the characteristic impedance of a symmetrical pi section. So in this one, first of all, we'll see this open circuited symmetrical pi section value. So in this one, these ports will be open circuited here. Now we calculate what is the total input impedance presented across your open circuited symmetrical pi section value. So at port 11 dash, let us assume that the input impedance is present across this port 11 dash is Z input impedance, and that should be equal to this 2Z2 is in parallel with the Z1. Again this Z1 is in series with the 2Z2. So upon solving this parallel combination, we will get the 2Z2 into Z1 plus 2Z2 by 2Z2 plus Z1 plus 2Z2. So this is nothing but a total input characteristic impedance of a open circuited. So it should be equal to 2Z2 into Z1 means 2Z1 Z2 plus 2Z2 into 2Z2 means 4Z2 square by Z1 plus 2Z2 2Z2 means we'll get 4Z2 here. So from these terms 2Z2 is a common term now, so I am making it as a common term. So upon taking this term as a common term, we are getting Z1 plus 2Z2 by 2Z2 of Z1 by 2Z2 plus 2. So therefore the total open circuited impedance of a symmetrical pi section is Z1 plus Z2 by Z1 by 2Z2 plus 2. Similarly, now we consider the short circuited symmetrical pi section value. Here we are simply short the second port 22 dash is a short circuited. Now we calculate what is the total impedance presented across the short circuited symmetrical pi section. So the total impedance presented across your short circuited symmetrical pi section is, so the input impedance Z input impedance is equal to 2Z2 is in parallel with the Z1 value, because here second port is short circuited, we don't consider this value here. So therefore Z0, the characteristic impedance of a pi section of which is short circuited, which should be equal to 2Z2 in parallel with the Z1 value, which gives you 2Z2 Z1 by Z1 plus Z2. So this is your short circuited impedance value, and this is your open circuited impedance value. Now we will see the term if we terminate the second port with any load, when we are going to calculate the total characteristic impedance of a symmetrical pi section value. So for this purpose, I am terminating this second port with a load value which should be equal to your characteristic impedance value. So this is a correctly terminated network. So this is your network, symmetrical pi section network terminated with a load. Now here we have to calculate the total input impedance presented across this port 11 dash. That should be equal to 2Z2 is in parallel with the Z1 value. Again this Z1 in series with the 2Z2. Again this 2Z2 is in parallel with the load impedance value, which should be equal to Z0. So therefore the total input impedance across this network is 2Z2 is in parallel with the Z1 value plus is in series with the 2Z2 value. Again this 2Z2 is in series is in parallel with the Z0 value. Okay, and we are saying it is a symmetrical network. Symmetrical network means whatever the impedance presented across your output terminal, that should be equal to your input impedance. So I'm making this term as equal now. So the Z input is equal to Z0. Now let's calculate this total characteristic impedance value. So here this 2Z2 is in parallel with a Z1. So this is a parallel combination of 2Z2 and Z0 now. So therefore the calculation it will become 2Z2 into Z0 by 2Z2 plus Z0. Nothing but this equivalent just like your resistance values R1 R2 by R1 plus R2 value. So upon solving this is Z1 value plus these values. So upon taking the LCM, we'll get 2Z2 is in parallel with the Z1 into this term. So it will become Z1 into 2Z2 means 2Z2 into Z1 plus Z1 into Z0 plus this total term 2Z2 Z0 by 2Z2 plus Z0. Again this entire is in parallel with the 2Z2 term. So take down the parallel combination. Already we know if any two impedance are parallel, so the combination is Z this impedance into this impedance by the sum of these two impedances. So this is 2Z2 into this entire time 2Z2 into 2Z2 Z1 plus Z1 Z0 plus 2Z2 Z0 by 2Z2 Z0 divided by these LCM, these as sum of these terms. So 2Z2 plus this entire term, no? So it will become 2Z2 plus of this entire term 2Z2 Z1 plus Z1 Z0 plus 2Z2 Z0 by 2Z2 Z0. Okay, now here we have to take down the LCM and we'll cancel out these terms. Okay, here I'm rewriting the equation here. So this entire time, this term as usual I write here. Now take down, multiply these terms and here in the numerator, in the denominator take down the LCM. So we will get 2Z2 into 2Z2 Z1 becomes 4 into Z2 square of Z1 plus 2Z2 into Z1 Z0 means 2 of Z0 Z1 Z2 plus this term 2Z2 into 2Z2 Z0 means 4Z0 Z2 square divided by 2Z2 plus Z0. Again in the denominator term take down the LCM. So you will get 2Z2 into this total term becomes 2Z2 into 2Z2 means 4Z2 square plus 2Z2 into Z0 2Z2 Z0 plus again this total term 2Z2 Z1 plus Z1 Z0 plus 2Z2 Z0 by. So this is a way to take the LCM. So the total term becomes denominator of 2Z2 plus Z0. Now cancel out these two terms. So now we'll get 4Z1 Z2 square plus 2Z0 Z1 Z2 plus 4Z0 Z2 square by here 4Z2 square. So here we have the 2Z0 Z2 term as well as 2Z0 Z2 term is 4Z0 Z2 term plus 2 into Z2 Z1 plus Z1 Z0. Now here we have to find out the Z0 value. Therefore I am taking them multiplying the cross multiplication. Applying the cross multiplication, so we will get Z0 term into this denominator term, this one into this term. So by upon multiplying this, we will get Z0 into 4Z2 square means 4Z2 square into Z0 plus this second term 4Z0 Z2 into Z0 means 4Z0 square into Z2 plus Z0 into 2 Z2 Z1 Z0, okay, plus Z1 Z0 into Z0 means Z1 Z0 square should be equal to 4 Z1 Z2 square plus 2 Z0 Z1 Z2 plus 4 Z0 Z2. Now cancel out this term. So here we have the 4 Z2 square Z0, 4 Z2 square Z0, cancel out these two terms. Similarly here we have the 2 Z0 Z1 Z2, here 2 Z0 Z1 Z2, cancel out these terms. So finally we have the total three values which are 4 into Z0 square into Z2 plus Z1 Z0 square should be equal to 4 into Z1 Z2 square. Here we have to find the Z0 value. So take down the Z0 square as a common term. So we will get 4 into Z2 plus Z1 which should be equal to 4 into Z1 Z2 square. So therefore Z0 square is nothing but 4 into Z1 Z2 square by Z1 plus 4Z2. Here from this one take down the 4Z2 term as a common. So here we are getting a Z1 Z2 by 1 plus Z1 by 4Z2. So therefore the total characteristic impedance of a symmetrical bisection is equal to under root of Z1 Z2 by 1 plus Z1 by 4Z2. Okay, hope you are clear this. Now here I am deriving the relationship between total characteristic impedance in terms of open circuit and short circuit impedance value. So in the starting we derived the open circuited impedance as well as short circuit impedance as these two. Just multiply this open circuited impedance with the short circuited impedance value. So that we know that, let's multiply open circuit impedance with the short circuit impedance. So open circuit impedance is Z1 plus 2Z2 by Z1 by 2Z2 plus 2. Write down this term here into multiply. In short circuit impedance is 2Z2 Z1 by Z1 plus 2Z2 here. So I'm rewriting these two equations here. I'm multiplying these two. So in the numerator term we have the Z1 plus 2Z2 term. In the denominator we have the Z1 plus 2Z2 term. So let's cancel out each other. So we get finally 2Z2 Z1 by Z1 by 2Z2 plus 2. So from this one take down the 2 term as a common. So we'll get Z1 Z2 by 1 plus Z1 by 4Z2. And we know that Z1 Z2 by 1 plus 4Z2 term is nothing but a Z0 square from the previous derivation. Therefore from here we can write Z0 is equal to under root of this open circuited and short circuited impedance value. Hope you are clear this topic. Thank you.